Our next presenter is going to be from UCR, and it's the nature-inspired technology. Again, this is technology that's available for commercialization.
All right, so good afternoon, everyone. My name is Nick Uragi. This is Jesus Rivera. We're both graduate students at the University of California, Riverside, but we're also representing today Nature-Inspired Industries, which is a company based on technology that was developed from the lab. And our PI, as well as the CTO of this company, is Professor David Caselas. So currently, in a variety of markets and industries, there's a high demand for new structural materials that are not only strong and tough, but also lightweight. So one great example of this is in the military, where current personal armor technologies feature these heavy ceramic plates that make up a large fraction of the armor. In addition, in industries like the automotive industry, as we know, our continued dependence on fossil fuels is leading to very serious global issues like climate change. And so there's really a great opportunity here to reduce that fuel consumption by having structural components for vehicles that are more lightweight. So we asked the question, how do we solve these issues? And in our research group, we actually turned to nature. So you may be asking, what can nature teach us about in making lightweight, strong, and tough structures? So we take inspiration from this crustacean called the mantis shrimp. It's an organism that's been around for hundreds of millions of years, but it's evolved this very interesting feeding mechanism called the dactyl club. It's a hammer-like fist that it uses to smash through the exoskeletal structures of the marine prey that it feeds on. What's incredible is that this organism is able to accelerate these clubs at the speed of a .22 caliber bullet underwater. And this organism is only about 6 inches long, and the fist itself is only a few millimeters in diameter. It's able to impact with forces up to 1,500 newtons repetitively. That's equivalent about 300 pounds of force. And what's also incredible is that it's actually moving so fast through the water that it's causing that surrounding water to boil in a process called cavitation. So over the past 7 years and through about $11 million of funding through the Department of Defense as well as National Science Foundation, we've really investigated this club material to try and understand what makes it so strong and impact resistant. And what we found is that it has this unique composite architecture called a helicoid. So it's a fiber reinforced composite where you have these unidirectional sheets of fibers that are sort of stacked and offset to produce this rotated, called a Bulligan structure. And it turns out, we found that through our research, is that this architecture of fibers allows for a tremendous amount of energy absorption. It's basically able to control the cracking at the local level within this material to absorb a lot of energy but resist catastrophic failure.
Thank you, Nick. Now I'm going to talk more about the technology and how we implement these ideas from the biological system to current composites in order to create lightweight, impact-resistant materials. So we currently have a patent on this design that we got from the mantis shrimp, and our goal is to manufacture these products that we have been doing. But here I'm going to talk more about the design of these carbon fiber composites and how they compare to current aerospace quasi-isentropic laminates. So here we can see two designs. One is a design inspired by the mantis shrimp, which is changed in pitch from each successive layer, compared to a 0.4590 composite in aerospace materials. So we tested these composites with ASTM standards that are rigorously implemented to see the mechanics of these materials. And what we were able to see is that this helicoidal design outperformed current manufacturing materials by basically displacing the force and deterring failure of the laminate. Here it shows depth measurements based on the impact of those materials, the helicoidal composite was able to dissipate the energy throughout the laminate instead of propagating it through the composite, which would cause failure. This slide highlights the end results of this test that show that the helicoidal materials outperformed the quasi-isentropic composites. And it highlights the fracture toughness that the change in architecture was actually able to achieve. So by using nature, we're able to improve the mechanical performance of these composite materials by changing the architecture of the structure.
And so one of the really interesting advantages of this technology is that we're really taking advantage of how these materials are architected. So there's no limitation on the material components, so we could really target a lot of different markets where they have different needs. Say they need materials that perform better in shear or in bending. We can apply the same architecture but use different material components, say fibers that are more elastic or resins that are more stiff for various applications. So we're Nature-Inspired Industries. Thank you again for the invitation here, and we'd be happy to answer any questions.
So now we have two mics. Is this on? Great, okay. So Chris is going to go ahead and take your questions. I'll stand up to the side. Questions? All the way in the back. Oh, one up here too.
So how much lighter and how much thinner is this new material compared to what's out there currently?
Sure. So basically what we found from these tests that Jesus mentioned earlier is that the composite materials show about a 50% improvement in this property called den depth. And so that's using the same quantity, same number of plies as what we're using in the industry standard. So that relates to about a 50% improvement in the damage resistant properties for the same weights or same amount of material. Or you could alternatively think of this as having the same toughness and impact resistant properties for about 50% of the weight.
Thank you.
One more question right here.
Just two questions, just to clarify. One, are you part of Nature-Inspired Technologies? Is that your group that y'all created? And two, are y'all working on other technologies for asking, like I said, I have an interest in spider webs and learn the strength, with my company. Can y'all deliver that as well?
Yeah, so actually, you mentioned spider silk. One of our projects that we're studying in our research group is looking at spider silk. So there are a lot of different systems that our research group is studying, and we sort of believe that our company or UCR can be like an incubator for a lot of these ideas that we can further develop in the company. Jesus and I are currently members of the company, but we're also graduate students. So our time is kind of split here, but we are both interested in pursuing this full time after we complete our studies.
Any more questions? Oh, okay.
Has the patent been granted, or is it just pending?
Yes, the patent was granted late September.
Any more questions? Everybody? You just wanted to make them run.
Hi. So you guys said that you're graduate students, correct? Okay, so were you involved with this company before you became a graduate student? Was this a part of your undergrad studies?
Sure.
And then
So
you decided to create the company, and what did that look like?
right. So I'm currently a fourth-year graduate student, PhD student. Jesus is starting his second year. This project, as I mentioned, started about 7 years ago. So the technology and a lot of the fundamental research was developed and published before either of us started, and only within the past few years, actually after I joined, was the company started. But actually the mantis shrimp is the what I actually studied for my PhD thesis. But we're studying different aspects of this material. Does that answer your question?
Any more questions? You mentioned at the outset the use of ceramic plates in existing protective armor. What, and I might have missed it in your presentation, what material are you proposing to build into this biomimetic architecture?
Right, so the materials that we used for the validation against the aerospace standards were carbon fiber epoxy composites. But like I mentioned, we really see the advantage of this technology as being the architecture of this component. So we could theoretically use that same architecture, but use different materials that have higher stiffness or more ductility. Does that answer your question?
Yeah, thank you.
Any others?
Yes, one more right here.
Oh, okay.
Does the process have any effect on carbon fiber?
Would you put the mic a little bit closer?
Does your process have any effect on carbon fiber?
Does it have any effect on carbon fiber?
Some products are made from carbon fiber. Your product that gives more carbon slab, certain thickness.
Right.
Does it have any application when you look at carbon fiber?
I don't really understand your question.
Could you speak a little bit louder into the microphone?
I'm sorry, what I meant is carbon fiber. Are you familiar with that?
Yes.
So does your research have any effect on carbon fiber?
So you mean research into the fibers themselves?
Yeah, when you produce carbon fiber,
Right.
does your product have any effect on production of carbon fiber in enhancing its capability?
Yeah. So so currently the materials we're using commercially available fibers, but we have additional research efforts where we are actually making our own fibers. And so there is a potential there to affect the carbon fiber market, where we can design new types of fibers that may influence how they develop their materials.
Great. Good round of applause for our presenters.